Okay, so I forgot to mention that I have made a new quiz. Well, this will be the last quiz. There it is. It's not under quizzes, but it's there. About MPI. I have been told that there's a problem with it, so don't take it quite yet, just yet. It's due July 23rd. I've got to fix it. I should get that done. I will get that done today, so you can take the quiz after that. Anyway, so today I want to talk about handling larger scale projects and even these smaller scale ones. I'm going to talk about the end body, so don't run away just yet. I know, what's funny is Canvas tells me how much you watch and which parts you watch, so I know when you stop watching. So yeah, don't run away just yet. I know it is kind of creepy, isn't it? It also tells me when you're taking a quiz, when you switch tabs and Google something, it doesn't tell me what you're doing. It just tells me you left the quiz and you came back, and it's funny. Anyway, so, okay. I'm going to talk about code organization. So, when you are trying to structure a larger piece of code, one that you can't fit all in your head, okay? Rule number one is write it down. I've already talked about that in the debugging. You got to write stuff down. You got to get it out of your head and onto the paper. The paper remembers things a lot better than you do, unless you get it wet, in which case it doesn't remember anything at all. So, but the main thing that you need to keep in mind when you are thinking about how to organize your code is what I'm going to call encapsulation. Okay, this term is often applied only in the context of object-oriented programming, but I'm going to generalize it a bit. And what the idea is that each piece of your program should encapsulate a specific idea, a topic, a duty, a responsibility. Okay, and the mechanism you use to encapsulate these ideas are vary across programming languages and across programming paradigms. You have object-oriented programming, where an object contains kind of a physical thing, like a car, for instance, or an animal, a cat, a dog. But that object then manages that dog. So then you could have another object called a pack, and a pack manages a bunch of dogs, for instance. A function could, like a square root function, has one job: take the square root of a number, and it receives a number and it spits out a number. Okay. Anyway, what this does then is it protects pieces of your code from each other. It keeps them from messing with each other. It provides an API, or the application program interface. It's the gate through which data passes. Okay, and if you want to build flexible and very powerful programs, ones that you can do a strong scaling test with and a weak scaling test with, you need to have these defined interfaces. And what this does is it reduces coupling. So coupling will always exist in a program and between pieces of a program, but strong coupling, and I spelled that all wrong. If two parts of your program are strongly coupled, then if you want to modify this one, you have to modify the other one. Okay, if the coupling is weak, you can modify one part of your program without ever having to touch the other part of your program. So it reduces your workload to have weak coupling or loose coupling. And that's done by having a good defined API, okay, and a good defined encapsulation. So there's a lot of ways to do this, but in general, when you get into larger projects, you're going to have multiple files. And so each file should have a topic. Okay, you can have multiple functions in a file. So you want to divide your code between the files. Each one should have a topic. Of course, you're going to need a header file if you're doing C and C++. And the reasons we do this is it helps structure your project because it keeps related functions close to each other and allows for function inlining by the compiler. It also can reduce compile times because if you modify one file, all you have to do is recompile that one file instead of recompiling the entire project. And so along with this, I want to talk about the static keyword and anonymous namespaces in C++. So I have here an example. Okay, this is just a C++ file. All right, so if we have inside of this C++ file, okay, first off, rule number one, don't do this in a header file. Okay, this is bad juju in a header file. But in a C++ file, you can say static int my variable equals 0. Okay, and what this does, the static keyword says that my variable is only accessible inside of this file. You cannot access it from another file. This is how C libraries like MPI work. Okay, they have a bunch of static stuff that they keep contained inside of their files, and functions inside that file can access the locally global variable my var. You can also do the same thing with functions. So this function is only accessible inside of this file. And that's how you prevent and protect yourself from namespace clashes or naming clashes, where you have, for whatever reason, you now have two functions called my function, and the linker really doesn't like that. And so you can prevent that with the static keyword and say this function is only accessible inside of here. Now, that's the C way to do things, and it's still around in C++. They did try and get rid of it once, and people got mad. I found out. So they brought it back. But this is more than the C++y way to do it. Okay, is by having what's known as an anonymous namespace, and I probably should have done some good code formatting there. Okay, so we have this namespace that has no name. It's called an anonymous namespace, and it does the exact same thing. So now if I have another function, now I can say something like that. Okay, so this anonymous namespace makes everything inside of it local to the file. Okay, it cannot be accessed from outside the file, which is a good thing. So that's one way of structuring and organizing your code and preventing access, encapsulating. You are surrounding these functions and saying they cannot be accessed from outside the file, and you're protecting them. Okay. So now give each function a task. All right? When you write a function, you should have a very clear understanding of what that function will do, what it will take in, what it will spit out, etc. So basically divide whatever you need to do into small tasks. Then write a function for each task. Now you can, of course, get really nitpicky, and in which case you kind of have an explosion of functions, and naming them all is kind of a problem. But what this does is it helps prevent bugs, meaning do not repeat yourself. The more times you type the same thing, the more likely you are to do it wrong. So if you have one place to do one thing, and you can always then access that one thing, you're less likely to have problems. And so, as an example, I'm going to show you how to break down the n-body problem. Okay? So let's go ahead and just clear all this out. All right, so I'm just going to write a little bit of pseudocode here. What are the tasks that we need to do in the n-body problem?
Generate random bodies.
Generate random bodies. Okay. What else?
Calculate the forces on these bodies.
Calculate forces. Okay. What else?
Step through time and do it again.
Step through time and do it again. Okay, so that says, to me, maybe a loop would be useful. Okay. Now, I'm going to break this down a little bit more. Step through time and do it again. What are the subtasks in that?
Calculate new positions. Calculate new forces. Calculate new velocity.
Okay. So calculate new forces, that actually is a subtask of calculate accelerations, right? Okay, calculate new forces. I'm going to break this down into calculate, how do we, the local n-body problem. Calculate the visitor n by m body problem. Both of those can be broken down into the two-body problem. Okay. And then, of course, permeating through all of this, we have the communication problem. Okay, can we break down the communication problem any?
Send positions, send forces.
Send positions, send forces, and then receive positions, receive forces. Okay. So, looking at this, generate random bodies. We only have to do that once, right?
Yes.
Does that, in this context, does that really need to go into a function?
What?
Generate random bodies up at the top.
Because you only do it once.
You only do it once, and we're only doing this project once, so maybe not. Okay. So probably doesn't need its own function. However, we do need to initialize everything. So we need to calculate forces. But don't we do that down here? So we do that twice. We have to calculate forces. So that's definitely a good candidate to be put into a function. And I'm not going to re-break that down because we've already done that. Calculate new positions. I would probably put that in a function. Calculate accelerations. I would probably put that in a function. Calculate new forces. Here we're going to have, I'm thinking, two different functions. The first one does the local, we have a function here. And this one calculates the local n-body problem. I would have this one do the visitor body problem. And both of those then reference the two-body problem. You calculate the force between two bodies. You have I and J. You calculate the force between them.
Force between 1 and 2, 1 and 3, 1 and 5, 6. Just separately.
Okay.
And then
Okay.
add them all up. Local n-body is on the processor.
Right.
Visitor is on the one that's being passed. On the ones that are being passed.
Oh, you pass it to them and they're calculating something.
Yeah, so two body is breaking it down to as simple as you can have it. Basically.
Yeah. Two-body, yes, the two-body is a subset of both of those. And so now that we've broken this, yes.
Sorry, do do you have to differentiate between calculate local and calculate visitor?
Yeah, you do. Why is that?
I don't know.
Because local, you have one array. Visitor, you have two.
What do you mean?
So you have, with the local,
Talking about positions, right?
yeah. So local, you have one array of all the bodies that are local to your process.
Okay.
Okay? And so you need to actually do a double loop through.
So when you're doing
All
the
of that.
visitors, you're doing the one that's on the local and the one that's on the visitor.
Right. So you have the visitor array. So now you have two different arrays.
To take in two inputs
And can you just
make
put
those
the
two inputs the same
one
thing.
in twice?
Yes, you could do that. So
But you have
that,
to make sure.
but then you'd have to have a copy of your data.
Right.
You'd have to always make sure that copy is up to date.
Would you? Can you not put the same thing in twice?
Yes, you can actually. You can put the same thing in twice.
You just have to
Because
make.
we're not like
But then
editing.
we have aliasing effects going on.
Oh.
And
You could keep a copy of it because you're going to be passing stuff anyways. So.
yeah, so you're right. You're right. You could pass them in twice, and you'd be fine. So yeah, that is good to know. I hadn't thought of that. So just in case you didn't hear that, what Robbie was saying was that these two here could actually be one function, and we're going to define the function something like this. It'd be void and body, and we'd pass in, I'm just making this up, the size of the arrays, and then we'd have the pointer to positions, first positions, pointer to the second positions, pointer to the first forces, pointer to the second forces. Okay? And so what he was saying is that this kind of interface actually covers both of these because we could call it, and you can't use minus signs, that doesn't work, so. And you would call it like this.
Well,
Yes?
yeah, but I mean, you're eventually gonna have an array or whatever you want to call it for the ones that are being passed to you, right? So you can
Right.
just store those in that array and replace them when
Yeah, and you
if
could
you're
do
worried
that.
about aliasing.
Uh,
You could initialize visit as local.
That's local.
Yeah. And so this one function, you can do it this way. I didn't, but you can do it this way. Because they seemed like two different problems when in reality they're not. Anyway, so this first way to do it here, this one covers the local because we're just passing in the same thing. And then the second one covers the visiting one as well. So that is good. And then we have the sub problem, which just takes in, I would say it returns some sort of struct maybe of we'll call it a vector struct, a vector2 struct. We'll call it body2 since we can't start with numbers, and then we take in the positions. And this is not technically correct, but
Can you return a struct in a function?
you can.
Didn't know that.
Yeah, you can treat a struct just like you would anything else. And so what this one does is it takes in two positions, it spits out the force between them. And you always have to use some sort of sign convention. Always going to be P2 minus P1 inside of that function. So that way you can make sure when you want to flip the sign on it, you can do that correctly every time. Alrighty, and then I would have a separate function for the communication as well. So, whoops. Anyway, that is my breakdown of the n-body problem. So, I would talk about in C++ and in a lot of other languages you have very similar concepts, but here we have namespaces. And namespaces are used to prevent name collisions and also lend, when you're reading the code, you're understanding where these functions and variables come from and what they're doing because you understand the concept of what the namespace is supposed to be doing. So the most common usage you've probably seen and never known what you're doing is this one. Okay? The standard namespace is everything that's in the standard library, which is ginormous, by the way. And by saying using namespace standard, you are importing everything from the standard namespace. In general, you shouldn't do this because this namespace is huge and you don't know what names you're actually importing. Okay. However, there's another variation where you can say using standard vector, and this imports just the vector class. And so now you could use it just as vector rather than standard vector. Okay, and that is more useful. It's safer, I should say. Not more useful, but it's safer. Because now we know exactly what we're bringing in. And as an example, there's a library I use. It's called Samurai. I wish they'd, actually put a U in there. And that would have been a cooler name, in my opinion. But as an excellent example of this, so here is the documentation for the Samurai library. Okay, and they have several. First off, they have an overarching Samurai namespace, and everything in their library is inside of that namespace. So when you're reading your code, you can say, okay, this is something from Samurai. And then inside of that, they have nested ones. So here we have the Samurai library, and inside of that, then we have these other namespaces. And they've organized this in such a way that this is the base namespace. Okay, it depends on nothing. The hierarchy depends on the toolbox. The transfer namespace depends on the hierarchy, which depends on the toolbox. PDAT depends on transfer. Math depends on PDAT. Mesh on math. Geometry on mesh, and so on. Okay, and so they've organized it in that linear fashion so you can very clearly differentiate and understand their organization because it is very straightforward. Now, a namespace.
If I do one in the middle, do I have to tell it to bring in all the ones up to that point that it depends on?
No, it does that itself. So if you only need geometry, you just say, I want geometry, and everything's taken care of. So as an example of this, let's say in this file, we can make a namespace. We'll call it USU because we're awesome like that. And inside here, we could have another namespace called engineering. And inside this, we could have another namespace called MAE. Okay, and we can put stuff in here. We could put stuff in here. We could put stuff in here. And then we would close them all like so. And it's useful also to just put a little comment like this, so you know what that closing bracket is linked to or should be linked to. It's a handy little tip. I kind of feel like I'm on Food Network giving cooking tips now. Make sure you pan the bottom of your pan so cleaning is easy. And then, so that would be the file blah.cpp. But we could open up another file. And in here, we can use the exact same namespaces and add stuff to them. Okay, so you don't have to put everything in a namespace in a single file, which is very useful for large projects. And so that way they're all cohesively linked together through the namespace, even though you physically have separated the functions and the variables and the classes and so on. Okay, I'm going to talk about object-oriented programming, since that's the big thing nowadays. Important to know, a class doubles as a namespace. Okay, works exactly the same way. Classes encapsulate and protect their data and their idea. In general, only they or trusted friends can modify the data, and that's done through the function interface. So you are not allowed to actually modify the internal variables. You have to use the functions that they provide in order to modify them, modify the state of the object. So classes also allow for inheritance. Inheritance allows creation of child classes, which you can then use to modify the behavior of the parent class. Okay, and this allows you to define a common interface or an idea of how this class should be used without you needing to add thousands of if statements throughout the code to define what happens in specific cases. And so you should think very carefully about how your class should be used. And again, I'm going to go back to Samurai, because Samurai is written in an object-oriented fashion. So let's look at the documentation here. Go back to the main page. Look at the classes. This is the class list. And I'm sorry, Ted, but this is why this is so scary. This is the list of classes that they have. This is object-oriented programming at its finest. So I want to look for, what would be a good example? Is that a thing? No, it's not a thing. What am I looking for? Let's go back. Let's click here. Class hierarchy. Sorry, this is on my other computer, so it's slow. Okay. Here we go. Here's an example. So we have a thing here called a box geometry. And we're going to pull that up. So box geometry is the parent class, and each one of these is a child class of it. And so you can see a box, we have something called a box. I'm not going to go into the details of this, but something called a box geometry. And we can then differentiate between a cell type geometry or an edge type or a face or node or outer edge or outer face. And they all have documentation on what the difference is between them. And they wrote it in such a way that you can actually add your own classes. So if you needed to do something slightly different, you can inherit from box geometry. And as long as you follow their documentation, which is really good, I might add, you can actually make it do something different by using your own class, which Samurai will then take that, because Samurai operates on box geometries. It doesn't care what all the rest of this stuff is. All it cares about is box geometries. And so you can make it do something different by adding your own child class, which is really good. And you can easily extend the library and make it do different things. So I got this in the wrong order, but an inheritance relationship defines an is-a relationship. So a Ford Mustang is a car. Okay, and so you could have a car class, and then from that you have then a Ford Mustang class, which says I'm going to accelerate faster, or I'm going to look dumber, or sorry. Whereas sometimes you have, instead of a is a relationship, you have a has a relationship. So a car has an engine, it has wheels. And so these would be member variables that you would put into your class. And those in turn, an engine, you could have a specific type of engine. I am a Ford Mustang with a Volkswagen Beetle engine, which doesn't make any sense, but you could do it in computer land. So, so when we're dealing with object-oriented programming, people have come up with clever solutions to hard problems, which they call design patterns. And there's lots and lots of these. I've looked at some of them a little bit, but I want you to know that they at least exist, and so you should at least kind of familiarize yourself with them. Probably the biggest two that are used, as far as I understand it, is the factory pattern and the visitor pattern. Okay, so the factory pattern, basically what you're going to do is you're going to tell a function or even a class, in more complex cases, a job to create other objects. That's why he's called the factory. And the point here is to provide a one-stop shop for getting an object of the correct child class. Okay, so you are not supposed to use new or any sort of creation method other than the factory pattern. And because what that does is it gives you a nice consistent way to actually get specific objects. And I've actually used this pattern in some of my code that I'm going to show you here. So I have this thing called a cart interpolation. And so anyway, if we're interpolating things, there's, of course, different ways to do that. And so what I've done is I have this base class called cart interpolation. And then inside of this base class, we actually have the create cart interp function. And what this function does is it spits out the correct order of accuracy that I have asked for. And so here is my order of accuracy. And then it returns, so if I want a 0th order of accuracy, it's going to return the constant child class. So here we define a new constant class, and we return that into this pointer. And you notice that what I'm returning here is actually a cart interp pointer. And then, so case, if I wanted a first order interpolation, it returns the trilinear class. And those are the only two I've defined right now, but this is a factory function. I don't ever actually have to type new constant anymore. All I have to say is, I want a new interpolation, and it spits it out for me, okay? And so that's an example of a factory. And Samurai is full of factories as well, but they're far more complicated because they do a lot bigger stuff than that. The other one is the visitor pattern, which is kind of cool. And this is to provide what's known as double dispatch. So let me draw on the screen a little bit. I don't actually have an example of this. I'm sure they use it in Samurai, but I've never found it. So, okay. No! Argue with my screen here. Okay. So let's say we have a child class. A parent class. And we have 2 children for this parent class. And let's say these are some sort of data structure. For instance, if we're looking at I'm thinking of like a CAD package. There could be different ways to represent the geometry in a CAD software. So this would be geometry 1, geometry 2. And then let's say we needed to output these things. So if we needed to output these to, so this is my inheritance relationship, and then there'd be two different plotting functions, one that spits out an STL file and one that spits out an IGES file. This one is an STL file and this one is an IGES file. Okay, so we'd have to basically write 4 different copies in order to actually get this program to run correctly. Are you following me so far? Okay. Now, what happens if we add another type of internal data structure? Well, he needs to do STL and IGES files, right? Well, what if we add another type of output? Well, now we got to add an output here and an output here and an output here. I mean, if we want, I don't know, a NURBS file. I don't even know if that's a thing, but NURBS sounds funny, doesn't it? You can see that we actually get an exponential explosion of work as we keep adding things. And so the visitor pattern, the idea is to actually reduce the amount of work that has to be done. So going back to where we were, let's draw our 2 children here for our internal representations of the data in our CAD package. And then we're going to define what's known as the visitor. And we're going to call this the outputter. Okay. And this one here has a function called plot. And he takes in the outputter. And so the outputter is the visitor. And the visitor has subclasses, okay? And this is the IGES class, and this is the STL class. And in here, all we have to do now is we're actually going to have 2 different functions. One that takes in the first type of data and one that takes in the second type of data. At the moment, it doesn't look like we've just added more work to ourselves by adding all these classes and things. But the idea here is that if we want to plot or output, then on this end, all we have to do is accept an outputter and then run the outputter, and it automatically figures out which one to use, okay, based on the inheritance relationship of the IGES file and the STL file. And so now if we add in a third type of data structure, we add him in here and here. And then if we add a different type of output, okay, then we can define 1, 2, and 3 right here. And if something is illegal, if it's not possible, well, then we can just, throw him out. And now you see we haven't needed to change at all this side of it. All we've needed to change is this side. And it reduces the amount of work we need to do. What we've done is we've separated the responsibilities of the output versus the data structure. And that's the visitor pattern. And it's, of course, there's lots of implementation details that I'm not going to get into. But these kind of design patterns exist, and people have come up with them because they are really the best way to do things in an object-oriented manner and solve these complicated problems, such as having to code this huge tree of stuff. And last of all, I just want to talk about there are lots of what are known as programming paradigms. Object-oriented programming is really the big one now, but there are others. First off, I'm going to talk about imperative programming. So what that means is we tell the computer exactly what to do. You will add 2 plus 2. Okay? And that's your most general form, I guess, is imperative programming. But then at a higher abstraction level, we have functional programming. And functional programming tends to be easier to understand because the idea is you have a series of functions and they're pure functions, and which means that they have no side effects. They take in something, they spit something else out based on what they took in. There was no modification of global variables. There was no input output, but you have to have that in the end. And functional programming tends to be easier to understand, making lots of little small functions that do one job and do it really well. Object-oriented programming for structuring your code and dealing with the objects instead of the what needs to be done. Declarative programming, in which you say what needs to be done but not how to do it. I've never actually done that myself. Procedural programming is actually a general form of functional programming because we write procedures, we write subroutines, we write functions. It's how we break things up. And it's also a form of imperative programming. These are all, related. Generic programming is where you use things like templates and the compiler figures it all out for you. Event-driven or data-driven programming is where you basically wait for something to happen, and based on what happens, then you do something. That's used a lot in GUIs because the GUI just sits there and waits for you to click on a button. And so when an event happens, such as you clicking on a button, then it will do something. Data-driven is where the program responds to the data. And so that can be a really powerful way to program as well. And each one has its pluses and minuses. Personally, I prefer a functional programming point of view with a little bit of object-oriented programming to help keep things straight. Because functions are easy to think about. You can say this function does X, Y, and Z, and you don't have to worry about anything else. You don't have to say, is the dog sick in this case? Okay. In object-oriented programming, you have to say, is the dog sick? I don't know, so I have to check. Whereas with functional programming, it's very straightforward.
What is the difference between functional and procedural again?
Procedural deals with subroutines and functions, whereas functional tightens that definition down to pure functions.
Okay.
You're not allowed to use subroutines.
One output.
Yeah, every function has one output.
Multiple inputs allowed.
Multiple inputs are allowed, but there's only one output. Functional programming also deals a lot with passing functions into other functions. So you can have a mapping function, and you give it an array of data, and then you give it a function. And what it does is it loops through the data and applies the function that you give it to each piece of data. Okay, and that is the main workhorse of functional programming, is being able to pass functions into functions and being able to do recursive function type things.
Can you pass functions into functions procedural? Or is that one function?
Yeah, but again, it's more of a philosophy than an actual set of rules. So in functional, all of these are philosophies more so than anything else. Yeah. And so with functional programming, the philosophy is write everything so that every function has one job, it returns one thing. Procedural, the philosophy is put everything in big blocks. Imperative is tell the computer exactly what to do. Generic is let the compiler figure it out, and so on. So that's why they're called paradigms, or you could call them philosophies. So anyway, those are things to understand when you're going through and writing down figuring out how to organize your code and keep things straight in your head. And I promise you, write it down on paper. Document it. It makes far more sense on paper. So anyway, that's my little lesson on code organization. Some little C++iness thrown in there. And I hope that helps, especially with the n-body problem. So anyway, that's all I got for you today. So we will talk to you guys later.